fellow at Caltech. His research aims to build AI that can understand and reason about mathematics. To that end, he has focused on using machine learning, especially large language models, to prove theorems in formal environments such as COQ and LEAN, which he will define for you. He has received the Siebel Scholar Award. Before joining Caltech, he received a PhD in computer science at Princeton, and he did his bachelor's at Tsinghua University, if I didn't mispronounce it, in computer science and mathematics. Welcome, Kaiyu.
Thank you, Stephen, for the really nice introduction. I'm Kaiyu, and I haven't updated the slides, but I recently left Caltech and joined Meta AI as a research scientist. So I'm really excited to talk to you about my work to build AI that can understand and reason about mathematics, or an AI mathematician. So please feel free to interrupt if you have any questions. And mathematics has been an important goal of AI since day one. In the 1950s, Alan Neville and Herbert Simon, who are the two AI pioneers, developed arguably the first AI program, Logic Theorist. So this program is an automated theorem prover that could prove 38 theorems from the book Principia Mathematica. Moreover, it pioneered concepts such as heuristics and search, which became central to symbolic AI. And then AI has evolved over 7 decades. Today, large language models, or LLMs, are predominant, yet mathematics remains a central challenge. Mathematics is often highlighted as one of the most important performance measures for LLMs. For example, GPT-4 outperforms most humans in the SAT math exam, and Clowder is evaluated on many benchmarks related to mathematics. So the enthusiasm for AI to solve math has also led to the AIMO prize. That's a $10 million prize for developing AI that can win a gold medal in the International Mathematical Olympiad. So why has there been such a long-standing interest in AI for mathematics? One reason is definitely intellectual pursuits, because mathematics is a hallmark of human intelligence, and achieving that has always been important for AI. But in addition, due to the foundational role math is playing, advances in AI for math will impact a wide range of things, like science, engineering, and also including finance. So given the importance of AI for math, the next question is, what is the state of the art and how to build it? So here is a very simple recipe. First, you take a large language model pre-trained on generic internet scale datasets, for example, Llama or other, or GPT-4 or other open source language models. And then you continue pre-train it on math-specific data. So those are like web pages from archive or online math forums like Math Overflow. So in this step, the language model becomes more specific in the domain of mathematics. And then finally, you fine-tune the model on a carefully curated dataset. So this dataset is usually much smaller, but also much more expensive. It consists of math problems with detailed step-by-step solutions. So researchers have built many math language models using variants of this pipeline, and it can be further improved in many ways. For example, you can always use a larger model or construct a larger and cleaner math dataset. However, an important question is, how far can we get? Is it possible to achieve human-level mathematics merely by scaling this up? And to answer this question, let's look at a few gaps between LLMs and human mathematicians. First, today's models are really good at elementary math up to the high school level, but usually not anything beyond. Because as we move forward towards college or even research level mathematics, the data becomes much more scarce, making it very difficult to train a data-hungry large language model. Also, checking the model's output becomes difficult. When the problem is not about calculating a number, but involves some kind of abstract mathematical reasoning, it's become difficult to tell whether the reasoning is correct or it's just wrong. And this is true even for human mathematicians, and it's partially why math papers take so long to review. So therefore, it's hard to evaluate the model's output or to provide any useful feedback for learning the model. And second, mathematicians do a lot of experiments and exploration. They formulate conjectures, perform calculations, and look for examples or counterexamples. And all these are later consolidated into the final solution, which then may look very nice, clean, and polished. However, if you only train the model on the final results, on the final solution, without this exploration process, this might be limited. And finally, we humans learn mathematics not by studying 1 million problems. We learn a clean and powerful set of rules and apply them consistently. In contrast, language models do not learn this kind of interpretable and verifiable knowledge. So these challenges lie between the current LLMs and human-level mathematics. I don't see how we could address them merely by scaling up the existing pipeline. But if scaling is not enough, what else do we need? I want to argue that one important missing piece is formal mathematics, which uses logic and formal language to express math in a way that is rigorous and checkable by computers. So it relies on a class of tools called proof assistants, also known as interactive theorem provers. And popular examples include Isabelle, Coq, and Lean. So they are conceptually very similar, at least for the purpose of this talk. So we will use Lean for illustration. You can think of Lean as a functional programming language that is very similar to Haskell, but it can be used to write not only conventional programs, but also mathematical definitions, theorems, and proofs. So we will see what do we mean by that. So with Lean, writing mathematics is like developing software, and this is a piece of code in Lean. And first, it defines the concepts of natural numbers. And then it defines addition between two natural numbers. And finally, it states and proves a few theorems about addition. For example, addition is commutative. A plus B equals to B plus A. So this is only one file in Lean, and files are organized into larger units, such as libraries and projects. And just like software projects, formal math projects can also be open sourced on GitHub and reused by other projects. So a notable example is Mathlib. That's the math library of Lean. It covers diverse topics up to the graduate level, including algebra, analysis, geometry, and currently it has 77,000 definitions, 142,000 theorems and proofs, contributed by over 300 developers. That's 1.6 million lines of code, and it's growing rapidly. So if we compare formal math to the traditional way of doing math, like using pencil and paper, formalization brings a few advantages that can potentially help AI to learn mathematics. And when we use AI to generate formal mathematics, the output can be verified by proof assistants such as Lean. It produces either a yes or no answer or sometimes more detailed feedback. And this is very important because first, it enables us to evaluate the model rigorously without worrying about hallucination. And second, the feedback can serve as learning signals to improve the model, which mitigates data scarcity. And more ambitiously, by grounding AI math reasoning within this feedback loop, we want the model to explore the mathematical space by itself. For example, it could come up with conjectures and try to verify conjectures. And during this process, the model can bootstrap its capability in math, grow a library of interpretable and formally verified knowledge, and even discover new math. So my research approaches AI mathematicians following this paradigm. And a central problem here is how do we generate formal math? So this problem can be divided into several sub-problems. First is theorem proving. Here the model is given a theorem statement and generates a proof, a formal proof. And second is autoformalization. The model is given informal math written by humans, for example, textbooks or papers, and it translates them into formal math. And third is conjecturing. Here, the model explores the space of mathematics theorems and generates conjectures that might be true and that might be useful. So in the rest of this talk, I will dive deeper into our recent projects on theorem proving and autoformalization. And then finally, I will briefly discuss conjecturing as a future direction. So we will start with theorem proving. And in this part, I will focus on Lindojo, published at NeurIPS last year, and briefly mention a related project called Link-Copilot, which is still under review. So the task is, given a formal theorem statement, we want to generate a proof. And note that generating the proof can be very difficult, but checking the proof is relatively easy because Link can tell you this proof is correct, whereas this proof is incorrect. So unlike many tasks in machine learning, here the goal is not to mimic the ground truth proof written by human, but the model is free to generate any proof as long as the proof can be checked by Link. Okay. So here then a natural idea is to fine-tune a language model, taking the current proof state as input and generating either the next step or the entire proof. And many prior works have used LLMs for theorem proving following this idea, but unfortunately, none of them can be easily reproduced or built upon. So first, many of these approaches rely on private datasets. Second, none of them have released the model checkpoints or code for training and evaluating the model. And third, theorem proving often requires a tool for the model to interact with Link or other proof assistants. But only some of those prior work has released this tool. And finally, the compute requirement for training the model ranges from 1K GPU hour to 48K, which is quite exclusive to industry labs. So in this work, we introduced Lindojo to address all these aspects. It provides tools, datasets, and models, all of which are completely open sourced. And our model is efficient and can be trained on a single GPU within a few days, which give researchers access to language model-based theorem provers with a low computational cost. So before diving into more details, let's see a very simple demo. Are you able to see my editor?
Yes.
Okay, so this is Lean. We are using Lean in VS Code. Here you see two theorems, theorem 1 and theorem 2. And for each theorem, you have a theorem statement. So this is a statement, and then followed by the proof. And this is a statement, and this is the proof. And right now, the two proofs are generated by humans, are written by humans. So I want to show how to use machine learning tools to help you write the proof. So first, our model can give you suggestions on the next step. For example, if I remove this step and I type suggest tactics, and so here on the right, you see the suggestions generated by the model. And you can click on one of them to use it in the proof here. And not only can you suggest only a single step, but you can also ask the model to generate the entire proof. For example, if you remove the entire proof here, and you type search proof, and here on the right, you can see the suggestions generated by the model. But however, searching the proof is very challenging, and it's not always going to be successful. For example, if you try it on the second theorem, you type search proof. I mean, you can wait some time. Well, it's okay. Actually, here it succeeds. But you see here, the reason it succeeds is there's a theorem used with the same name in Mathlib. So that's kind of like cheating. But even when it does not succeed, it's possible to write part of the proof by yourself. Like you can write the first step, and then you can do such proof here. So here, the model is running locally on my laptop, so it's very easy to install and use. You don't need a GPU to use it. You can run it on CPU, and it's a tool called Lean Copilot. So you can add Lean Copilot as a dependency to your Lean project, and you import it here. And under the hood, Lean Copilot used the models we built in Lean Dojo. So I'm going to use this demo as a roadmap. Like for the rest of the theorem proving talk, I will try to explain what's under the hood of this demo. So let's go back to the slides. So first is generating suggestions for the proof steps. Here we've seen suggest tactics. But under the hood, what happens is if you type suggest tactics, it will get the current proof state, especially the current goal, and feed it into a language model for generating suggestions. And here you can use beam search or other sampling algorithm to generate multiple candidates. I'm showing 3 candidates here. And proof steps like this, they may use existing definitions or lemmas as premises, highlighted in the red color. And usually getting those premises right is often the most challenging part in theorem proving. And following prior work, our baseline model here is just a transformer language model that directly maps the state to the proof step. And in particular, we choose a model called ByT5, which is a variant of T5 with about 300 million parameters, which is fairly small in the modern standard. And in practice, this works quite well. But here it has one problem. So this baseline model has one problem, is it only sees the current proof state, but it has no knowledge of what premises you can use. And it can still use the premises if it memorizes names during training, but memorization is inefficient and difficult to generalize. So therefore, in this work, we introduced a model called reproval, retriever augmented proval. So our model explicitly retrieve premises from a large math library and use them to augment the proof step generation. So here we have a proof state in red, and we have a library of premises. So first we embed the state and each premise into vectors. And then we calculate the cosine similarity between the state vector and each premise. And then we can use the similarity to retrieve the most similar premises. And finally, we combine the retrieved premises with the state and use it for generating the next step. So here there are two parts. So we use a method called dense passage retrieval for selecting premises. And we use the BT5 model for generating proof steps. And these two parts are fairly standard and they are trained separately. We first train the retrieval and then given the retrieval, we train the generator. So however, the model challenging here is how do we get the training data for training the model? Because for training the generator, we need pairs of proof states and the next step. And for training the premise retrieval, we further need the entire library of premises. And we also need to keep track of where each premise is used and where each premise is defined. And Lindojo provides a general tool for extracting this kind of data sets from Lean projects, including but not limited to MATLAB. And it relies on a feature called metaprogramming in Lean 4, which gives you access to Lean's internal information, such as premises location and also abstract syntax trees. I won't go into too much detail about metaprogramming, but really want to emphasize that support for metaprogramming is really what makes Lean promising compared to other proof assistants for machine learning. So for this specific study, we extract a dataset from MATLAB. It contains about 100,000 theorems and proofs, and together with individual proof steps and premises. And we use this dataset for training the reprover model that can generate suggestions for proof steps. So now we are able to generate proof steps, but then how do we find complete proofs? It turns out we can easily find complete proofs by combining proof step generation with search. Say we have this initial state in red, and the model generates two candidates for the next step. And we can execute these two candidates in Lean, try to get the next state. And then we can do that repeatedly. So by doing so, we generate a large number of paths. And our goal is to search for a path from the initial state to a solved state. And this path is essentially a proof. And here, the search algorithm can, we can use any classical algorithm, like best first search or Monte Carlo tree search. So you have a lot of choices here. However, regardless of what algorithm you choose, that's a technical challenge is how your model in Python can interact with Lean programmatically. So using Lindojo, you can turn any theorem in Lean into an environment in Python. So here is how it works. So assume you have a theorem in Lean like this, and you have the original proof. So first we replace the original proof with a special proof step called REPL. And you know, proof steps in Lean, they usually have predefined behavior. But here we implement this step to have no predefined behavior. What it does instead is to perform I/O, which provides a command line interface for controlling its behavior. And once you have a command line interface, it's easy to wrap it in any language, for example, Python. And so this interface allows our machine learning model in Python to access and modify Lean's internal state. So let's look at some experiments. We use about 100K proofs for training and 2K theorems for testing. All of them are from MATLAB. And in testing, we give the model 10 minutes. And the model have to prove the theorem in 10 minutes, and we measure the percentage of success. And our main method is best first combined with proof steps generated by reproval. And we compare it with a few baselines. One baseline is tidy, which is the built-in proof automation in Lean. So tidy it's purely based on heuristics and search. There's no machine learning in tidy. And a second baseline is we replace the proof steps generator reproval with GPT-4. So we give GPT-4 a state and we ask it to generate tactics. So here are the results. The y-axis is the success percentage. So higher is better. And the x-axis are two different data splits. In the random data splits, we just split the theorems randomly into training and testing. And in the novel premises data splits, we split the data in a way that the testing theorems require you to use a novel premise. So that's essentially makes the testing set more challenging. As you can see, the numbers are usually lower there. And different colors are different methods. So first, if you compare gray and yellow with blue and green, you see that reproval, either with retrieval or without retrieval, performs much better than baselines like tidy and GPT-4. And also, if you compare gray with yellow, you see that adding the retriever provides a further performance improvement. And so that's the result. And finally, as we've seen in the demo, the models in these projects can be used directly in Lean, using the VS Code interface through a project called Lean Copilot. And so in building Lean Copilot, it involves two challenges. So first, we need to run the model in Lean. But in Lean, we don't have a library for deep learning. For example, there's no PyTorch in Lean. So how do we run the model in Lean? And this is achieved by training the model in Python and wrap the model in C++. And then we can run it in Lean through Lean's foreign function interface, or FFI. And a second challenge is most Lean users do not use GPUs in their regular workflow. So we really need the model to be efficient enough on consumer CPUs, like on my laptop. So we solve this challenge by using an efficient inference engine called cTranslate2. So we have open sourced everything related to Lean Dojo and Lean Copilot, and our models are on Hugging Face for download. And Lean Copilot is currently the second most popular package written in Lean, and it's only next to Mathlib. So I want to conclude the theorem proving part with a user testimonial from Kevin Buzet, who is a math professor at UCL. I added Lean Copilot as a dependency for the repo I'm using in my undergraduate class, and it really can do a bunch of the problems, sometimes in a totally different way to model my solution. I also tried it on a question someone asked on the Lean Zulup chat, and it solved that too, and very quickly. So Kevin has been very critical of AI for theorem proving, but now at least he's open to try future versions of these tools, because as he commented, who knows what language models will be capable of in the future. And so that concludes the theorem proving part, and anyone has question before we move on to the next part?
There is one question in the chat that I asked Jen Hookadin to ask aloud, but you can see it also. Just a second. Do you see the chat, the attendee questions?
I see.
Jen, go ahead and speak because you have you're enabled with the mic.
Yeah. Hello. Greetings. I hope you can hear me. Well,
Yes.
I can hear you.
You said in the beginning, well, basically you already answered that you have connected the theorem provers with the language models. I was just in the beginning, I was surprised that there was a scarcity of data math data when in terms of language models, because I've been with 1% coverage, I've been following the Lean prover for some years now, on and off. So it's really interesting to see your work combining all this into one package.
Thank you.
Maybe I should ask you that why is it so difficult for the language models to find the proofs? And can you maybe elaborate a bit about the in quality wise, what is the search pace like?
So I think one thing make it difficult is some of the proof steps can be very complex. So here you see the three proof steps. Each of them has a premise that's a name of a existing lemma. And so because there are so many existing lemmas you can use, here the search space is very big. And also these three proof steps are already quite simple proof steps, because in Lean you can also give a step, you can also have a arbitrarily complex term in the proof step. And it's very difficult for language to compose those terms correctly. And in practice, we find that language models are usually better at producing short and simple proofs. And if the proof is long and if there are a lot of tactics involving these complex terms, usually it doesn't work. Does that answer your question?
Maybe a follow-up. Can you use these symbolic systems to generate math-based language data for language models? And has that been done, or what is the situation?
I think that's a good question. I don't think there are a lot has been done. Because a challenge is how do you combine language models with more symbolic components? I think adding the retrieval is, in some sense, a step in that direction. Like you use language model to generate proof steps. So whenever you want to generate a premise, you use a retriever to do a lookup to see what premises are already there. But beyond that, we do need more ways to see how this kind of symbolic behavior can be encoded into a method based on language model.
Okay, thanks.
Okay, thank you. And then that's the theorem proving part, and let's go to the next part of this talk. So far we've been talking about theorem proving in formal math. So however, only a small part of human mathematics has ever been formalized. If you compare MathLib to the body of math knowledge developed by humans over centuries. So next, I will talk about autoformalization. That's a task that goes beyond formal math and taps into the space of informal mathematics. So in here, I'm going to present our recent work published at ICML this year. And so currently a major bottleneck of formal math is first you have to manually translate from informal to formal. For example, from math textbook and papers into Lean. And so currently it's manual, but autoformalization involves doing this translation automatically. And if you can do that, not only can you remove the formalization bottleneck, but if you consider from AI perspective, autoformalization really enables the AI formal mathematician to understand human written math. And autoformalization has two subtasks: autoformalizing theorems and autoformalizing proofs. For theorems, the model is given a theorem statement in natural language and outputs the corresponding formal theorem. And for proofs, the model outputs the formal proofs given everything else, basically given the theorem statement, either formal and informal, and also given the informal proof. And when autoformalizing theorems, a major challenge is how to evaluate the results. So here, the informal theorem says there exists an infinite number of primes, and the formal theorem says for any natural number n, there exists a prime number p greater than or equal to n. And you can tell it's a very straightforward formalization, and it's correct. But it is not the only correct formalization. For example, you can change it to p strictly greater than n, or you can restrict n to be also a prime number. And all three theorems here look different, but they're essentially the same thing. And it's easy to find many more equivalent theorems here. So if the model outputs one of them, how do you know it's correct? So you may say, oh, I want to have a ground truth, and I want to check whether the model's output is logically equivalent to the ground truth. Unfortunately, this kind of equivalence checking is computationally intractable in practice. So therefore, prior work has resulted to either using humans to evaluate, which is very slow and very expensive, or using proxy metrics such as the BLUE score, which is very inaccurate. And without a reliable way to automatically evaluate it, it's really difficult for machine learning to make any measurable progress on this task. So that's the challenge in autoformalizing theorem statement. And how about proofs? And a challenge there when we formalize proofs is informal proofs written by humans have a lot of gaps. And some of the gaps are explicit. For example, mathematicians often say, oh, this is left to the reader. And there are also other gaps that are more implicit, which we will get into later. But in contrast, formal proofs must be gap-free in order to be checkable by computers. And therefore, auto-formalizing the proofs often requires the model to fill in all the gaps, which can be quite challenging. And by now, we've seen two key challenges in auto-formalization. For theorem statements, there is no reliable automatic evaluation. And for proofs, the model struggles with fill-in reasoning gaps. And in this project, we want to address both challenges. And this sounds quite intractable. But one lesson we learned here is things intractable in general can often made tractable if we pick a restricted but interesting enough domain. So here, the domain we choose is Euclidean geometry. It's one of the oldest branches of mathematics and has been used to test humans for 2000 years. And recently, it has also received a lot of attention in the AI community due to DeepMind's alpha geometry work, which can already solve some IMO geometry problems similar to the level of gold medalists. So, and in this work, we show Euclidean geometry can also serve as a controllable domain for autoformalization. And we construct a Lean Euclid, which is a benchmark for autoformalizing Euclidean geometry. It consists of geometry problems from Euclid's elements and other existing datasets. So here is one example problem. For each problem, we have the informal theorem statement and the proof and also the diagram. So this is proposition 1 from Euclid's elements. And when constructing the benchmark, we manually formalized the problem into formal theorems and proofs in Lean. And this formalization process is not directly related to AI, but it's aesthetically very pleasing because to our knowledge, this is the first time Euclid's proofs are formalized faithfully in a proof assistant such as Lean. And here, faithful, it means there is a direct correspondence between the informal proofs and the formal proofs. So, and during this process, we did find a few interesting errors made by Euclid. And here is an example where Euclid made an error. I'm not sure if we have time to cover it in detail, but at a very high level, on the left is proposition 24 in Euclid's Elements, and it has a diagram and it has a proof. In the proof, Euclid kind of assumed the diagram looked like the one on the left, which is correct. But when formalizing the proof, we find that if the diagram instead looks like this, if you use the diagram on the right-hand side, Euclid's original proof no longer works, and you have to fix the proof in some non-trivial way. Okay, so let me skip the proof. So in this Euclid benchmark, it has two key advantages when it comes to autoformalization. So first, in this benchmark, we can evaluate whether an autoformalized theorem statement is equivalent to the ground truth. Remember that I said this equivalent checking is intractable in general, but we show that if you restrict to the specific kind of theorem in Euclidean geometry, by having domain knowledge and using automated reasoning, it's actually possible to do this equivalence checking. And second, in Euclid, we can fill in reasoning gaps in the proofs automatically. And this is because in Euclidean geometry, there is a well understood type of reasoning gaps, which we will get into later. So this is how we do equivalence checking between two theorems. And so given two theorems, T1 and T2, we want to know if they are equivalent. And what we did is we tried to use SMT solvers or satisfiability modular theory solvers to prove their equivalence in both directions. So first we try to prove T1 implies T2, and then try to prove T2 implies T1. And if we can prove both directions, we conclude that they are equivalent. And then we come to these reasoning gaps in proofs. And so we address a specific kind of reasoning gaps that's very common in geometry called diagrammatical reasoning gaps. So let's see it through an example. So here this is proposition 1 in Euclid's Elements. It says, given 2 points A and B, we can construct an equilateral triangle. And then here is the proof given by Euclid. It's very straightforward. So first you draw a circle centered at A and passes B. And then you draw another circle centered at B and passes A. And then you take the intersection and name it C. And then finally you connect everything, and that's an equilateral triangle. I want to ask if anyone disagrees with this proof or find any issues with this proof. Okay, no. Then the problem is, let's go back to the previous step. So when picking C, did we ever prove C actually exists? How do these two circles actually have an intersection? It turns out the two circles intersect. It does not follow from any axioms in Euclid's Elements. And no one bothers to prove it, including Euclid himself, because it's just obvious in the diagram. And so this is what we call diagrammatical reasoning gaps. And they're just ubiquitous in geometric proofs. Usually you don't think it's problematic because, I mean, that's okay. But it becomes problematic if you want to formalize this proof in Lean or in any other rigorous formal mathematics language. Because when you do that, you first have to define what does it means to say, oh, this is obvious in the diagram, because there's no diagram in Lean. And so it turns out philosophers have studied this problem and proposed a solution. In 2008, Avigat et al. Who is now a professor at CMU, introduced the formal system E. So in the formal system E, they tease out a set of like unspoken axioms, and they call it diagrammatical rules. And they model diagrammatical reasoning as logical inference using diagrammatical rules. And if you pick one of the rules, you see it's very, like, it's just like a trivial facts. Like if you look at the first one, center unique, it just means a circle only has one center. It cannot have two different centers. And so there are all these kind of very trivial rules, but when using this trivial rule to do logical inference, you can model what is obvious in the diagram. And so this formal system E, it was proposed as like a philosophical framework, but it was never instantiated computationally. So part of our contribution here is we implemented this system in Lean, and we designed a automated reasoning engine for actually carrying out this diagrammatical reasoning. And the engine is also related on, or is also relying on SMT solvers. So let's put everything together here. In Lean Euclid, we have informal geometry problems and a ground truth formal theorem that's annotated by humans. And when autoformalizing theorems, the model produces an autoformalized theorem statement. And we can check if it's correct by checking the equivalence with the ground truth using SMT solvers. And when autoformalizing the proofs, the model gives you a proof. And we send the proof to Lean, which identify a list of reasoning gaps. And then we use the SMT solver to try to fill in those gaps automatically. And the proof is accepted if all the gaps can be filled. And this result will tell you if the proof is correct. So let's see some experimental results. Here, our main contribution is proposing this framework and also set up the evaluation. So the models here, the evaluation are relatively simple. It's basically GPT-4 and the GPT-4 vision. And we use few shot prompting, which means we give GPT-4, or we give the model like 3 or 5 examples, and we ask it to learn from those examples. Then, so here is autoformalizing theorems. So higher is better. You see a few trends. One is if you go from 0 shot to 1 shot to 5 shot, which means if you give the model more example, it can learn better. And another trend is if you compare green with blue. Green is better because green is GPT-4 vision, so it has access to not only the text, but also the diagram, which shows if you give the diagram to the model, it can do better in Euclidean geometry. So this is similar to humans, I guess. So that's autoformalizing theorems, and we also have results for autoformalizing the proofs. I won't explain it in details because the stories are exactly the same. Basically, more examples helps, and adding vision helps. And here, I think it's the main takeaway for this specific project. So we address 2 challenges in autoformalization. One is autoformalized theorems are difficult to evaluate. The other is autoformalizing proofs requires you to fill in the gaps. And we show that they can all be addressed if you restrict to a particular domain and if you have domain knowledge as your leverage. So any question about autoformalization before we go into the final part?
Could you take, Kaiyu, can you see the comments? Do you see any comments to which you want to reply now? I've upgraded several commentators to wait until you've finished, but are there any that you want to answer now?
Sorry, I cannot see it because I'm sharing the screen.
Oh, okay. Well, let's say, let's put it this way. The ones who have been upgraded to, do you want to ask one of your points now? But not something that's going to prevent Kaiyu from finishing his talk. So I'm asking this from Sayara Islam, from Steve Hansen, from Julia Zimmerman, and also again from Jan Hukkinen. Anything that you want to hear and have answered right now? You can turn on your voice and say so. They all seem ready to wait till you finish your presentation, Kaiyu, which is it's very clear. It's extremely clear what you're saying.
Is that a question? Sorry.
No, I'm just saying everything is very clear so far.
Okay, thank you. And we're close to the end actually. So finally, I want to just very briefly discuss conjecturing as a future direction. Let's go back to this diagram. So you consider the scope of mass knowledge. As the smallest rectangle is formal mass. You can think of it as the mass in MathLib as people has already formalized. And a larger rectangle is the informal mass. You can think of it as the human mass knowledge over the previous 2,000 years. And I would say an even larger space is the space of potential mathematics you can do or you can discover. So if you work on theorem proving, you are essentially restricting yourself to formal math because the input is a formal theorem statement and the output is a formal proof. And if you do autoformalization, you kind of bridging informal math and formal math. But what if you really want to go beyond what humans can possibly do? I guess it sounds not realistic right now, but what if you think in longer horizons, like in maybe 1 or 2 decades or even longer? I think what must be done there is the model must be able to generate conjectures or what we call conjecturing. Because only if the model can generate a conjecture and try to verify that conjecture, can we discover new theorems and proofs that humans don't know yet. And actually we've already seen some work in that direction, although I'm not sure if they are framed in this way. So I want to consider alpha geometry, and I think it's highly related to conjecturing because I'm not sure if you are familiar with the approach, but at a high level in alpha geometry, they generate 100 million synthetic theorems and proofs. And once they have this huge data set, they use it to train language models. And this process of generating 100 million problems is conjecturing. Because even if you collect all the geometry problems that humans have written, you collect all problem sets, all books in the library, I guess it's not going to be 100 million. But if you want to train the model to be this good, it's necessary to have an algorithm that can give you essentially an unlimited number of problems as what's done in alpha geometry. However, a problem is the specific method they use to generate these conjectures is just very highly specific to Euclidean geometry. What they do is essentially they try to sample a lot of things, like sample a few points, sample a few lines, sample some circles, some triangles, and then do some filtering and then do some automated reasoning on this diagram, and then that gives you a problem and a proof. But this obviously this only works for Euclidean geometry. So one very interesting challenge in the future would be what are the other domains that are still feasible but interesting enough for we to study conjecturing? Or can we generate conjectures in in a large number of domains for general mathematics. And so, and another question in conjecturing that's worth investigating is, so what is a good conjecture generator? So how do we even evaluate success? So obviously, we want to consider correctness. That is, the generated conjectures should be correct. Or sometimes if we don't know if it's correct, it should be at least plausible. Because if the algorithm give you a lot of conjectures and they are just obviously wrong conjectures, then that's not useful, right? However, only correctness is not enough. Because even if you have a algorithm that can generate you a lot of seemingly correct conjectures, they are seemingly correct, but they can be totally trivial. For example, they can be 2 greater than 1, 3 greater than 2, 4 greater than 3, and an infinite number of these conjectures. All of them are correct, but they're just useless. So therefore, a central question for investigation is how do we measure the usefulness or interestingness or even the beauty of the generated conjecture? So that concludes today's lecture, and I'm happy to take questions. Thank you.
Was excellent. I think you're rivaling the last prize that we gave for the best talk so far. This is like the theorem for infinite number of primes. I'm going to ask people in the order that they posted their questions. Julia, you get first crack.
Hello, thanks so much. So I was wondering, so for one thing, different mathematicians have like different styles in their proofs. And I was wondering how much of that can be disentangled in the proofs for the LLM. Like, can you get sort of just can you get just the bits that have to do with the structure of math itself out from the personal preference, or yeah?
Yeah, I think the short answer is in the current state of LLM for theorem proving, we don't distinguish between different proofs of the same theorem. So that's related to a technical detail in Lean. So in Lean, it has this property called proof irrelevance, which means if two proofs prove the same theorem, they are essentially treated, they're not distinguished in any way. But I think that's a technical concern. But in the future, we might, if we want to push further in auto-formalizing proofs, for example, given a proof written by a mathematician, we want to use it as a inspiration for the prover. In that case, the style of writing proofs and also different ways to write the proof might become important. But right now, I would say it's not there.
Oh, okay, cool. And like for the training data, it sounded like you used just like a web-based corpus, like it has a lot of information in natural language as well, not just math. So like what would happen to the model if it only trained on like formal proofs? Because for people, we seem to need like the scaffolding of human language to learn math.
So here in the work I'm presenting, the model is only trained on formal proofs, because even for example on the slide on the left is like a Lean source code. In practice, there may be some natural language as comments in this source code. People may drop comments here and there, but it's not written in a systematic way. So then we decided not to utilize this kind of information. But I think maybe a more reasonable and more promising approach is if you use a larger model like GPT-4, it has already seen a lot of math knowledge in training, so in its internal storage, and then presumably that that part of natural language math can be utilized when you ask it to generate formal math.
Very good. Next question, Sayadas Islam.
Hi, I really found the talk interesting. I've been wondering this, like, in the other talks, people have argued that LLMs might not be just a stochastic parrot, like it actually understands what it's trying to produce. So, if that were the case, then why would we need the proofs to be converted to formal mathematics? Instead, why don't we just have the input directly be the informal proof, and then it outputs an informal proof as well?
One thing that because if the output is informal proof, it's very difficult to check whether the informal proof is correct. So you can, I mean, you can only use humans to check it, but that would be not scalable. But if you do it in a formal proof, as long as the model outputs a formal proof, the environment can give it feedback like this proof is correct, or maybe this step is wrong. And you can use this feedback for evaluation and also for improving the model.
Very good. Steve Hansen's next in line. And a side remark, Brendan Considine had a question, and then I upgraded him to panel, which he didn't want to do. So Brendan, if you want to ask it, then please ask it again in comment, and then I can read it out. Steve Hansen, go ahead. There's nothing coming from Steve Hansen. He tried. I'll ask him to. Oh, goodness. The trouble is that I had all these comments and then they disappeared when I did the upgrade. Oh, yes, I found them. Okay. I have Brandon's point. Hi, Kaiyu. Thanks for the nice talk. You're going to go ahead and do it? Oh, go ahead.
If you want, yeah, I can. So I enjoyed the talk. Thanks, Kaiyu. I'm just curious about, you know, if you can sort of characterize the generalizability of Lean Copilot in terms of like propositional proof complexity or automatability, and how would you compare your solver with more classical solvers in decidable theories? Can you compete with, you know, maybe satisfiability, and how do you position it generally in terms of more expressive or less expressive theories? Thanks.
I see. So the first question is how general Lean Copilot is. I would say it depends, because in the current version of Lean Copilot, the model is fixed. It's trained on a specific version of MATLAB. And if you do it in this way, the model may become outdated. So, for example, after a few years, if you don't update the model. And another issue is if your project is just very different from MATLAB. For example, if you are formalizing a specific branch of mathematics that's not in MATLAB, and if you try to use Lean Copilot as like an all machine learning method, if your problem is very far in a very different domain from the training data, usually generalization would become a concern. I would say there are ways to mitigate this. For example, we can constantly evolving the models, like retrain the model and retrain it on not only MATLAB, but also on all other repos we can collect online. So that's probably the easiest way to try to mitigate this thing. But I would say it requires more like engineering than research. But there are also deeper research questions, like how do we train a model and generalize to other domains? I think that's that will be less certain what is the right way to do. So that's the first question. So I think the second question is, how would you compare Lean Copilot with like automated reasoning tools like SMT solvers and set solvers? Is that the question?
Yeah, I mean, they also have refutations as well, right? So if it's unsatisfiable, then maybe there's a short proof of work.
Yeah, I would say, for example, taking SMT as an example, SMT is very good at the particular kind of problem it can encode. I mean, only if the problem has in a few real numbers and integers in this series, then you can apply SMT solvers. But in more general and more abstract mathematics, like college level or beyond, usually the problem is not just about a few real numbers and a few simple operations. In that case, SMT may not apply, at least not apply to the entire problem. It may be applicable to a subproblem. And also, I would say it's you can actually combine link copilots with SMT solvers. Like you can write a specific a concrete tactic for calling the SMT solver, but you can embed this tactic within the search loop in link copilot. So in this way, link copilot can use SMT solver as a tool. So I would say they are pretty complementary, and there are a lot of ways to combine them.
Very good.
Thank you.
I've located Steve Hansen's comment. He's been having intermittent technical problems. Some days it works and some days it doesn't. But I found it, he said, it's unclear how the training is done. What is the LLM trained on? The steps of the proof, developing a proof navigation, or hypothesis space? In what sense is this really learning to prove anything similar to a human?
So the LLM is trained on, I think it's easier to explain our baseline. So our baseline LLM is trained on a pair of state and proof step. So you have a lot of pairs. You extract these pairs from human written proofs. So each pair is a state, proof step, and you train the LLMs to predict the proof step given the state.
Okay, he can't reply because he's technically disconnected. Could you, now I have an anonymous, I don't know if it's the same anonymous attendee that has made a lot of good remarks throughout. It could be just a generic thing, but this anonymous attendee is, could you please define what you mean by restricting to a domain? Is a domain a finite system of definitions and axioms? Would, for example, Euclidean plane geometry be an example of a domain with Euclid's axioms? Then there's another one from him, but answer that one first, please.
By restricting to a domain, we mean we only deal with, for example, Euclidean geometry problems, or maybe another domain is elementary number theories, or maybe elementary combinatorics. And more technically, for example, here we focus on Euclidean geometry, then basically all the theorems takes a specific form. Let me try to find an example. So here the other forms of the theorems. So basically it's all like if you have some point, some circles, and some lines, if they satisfy some relations, then you have some conclusions. So all theorems look like this. But in general, not all mathematics theorems look like this. And so by restricting to this domain, I just mean we can make this kind of assumptions on what the theorem might look like and what the proof might look like.
Good. Now, I don't know if this is the same anonymous attendee, and I can't speak for him or her, but here is two proofs could be based on completely different sets of background results used. For example, the Pythagoras theorem has many proofs based on just cut and paste constructions involving a small number of triangles and rectangles. But there are also proofs based on infinite subdivisions of the triangle and summing a geometric series. In what way would be the resulting formal proofs related?
So it depends on, so I think the question is just there are many different proofs to prove the same theorems. I think then it depends on what your task setup. In theorem proving we study, we don't distinguish between different proofs. So as long as the model find a proof that can pass the link checker, we treat it as a success. But when auto-formalizing the proofs, because the model is given the informal human written proof, in principle it should output the same proof as like the formal version of this proof to link. But also I think a caveat there is that's what it's supposed to do. But in practice, we don't actually check if the proof is the same. So theoretically the model could output a completely different proof, although I don't think there's a reason for it to do that. The reason we cannot check is basically this check has to be done by humans. There's no way to automatically check it.
Well, to a cognitive science audience, that's a little bit ambiguous. I mean, is there anything that a human can do that is cognitive that is not something that you could do somehow algorithmically or with algorithms and statistics?
I think there are a lot of things. I wouldn't that human mathematicians do. I wouldn't say computers cannot do it. I would say just state-of-the-art methods haven't been doing it. I'm not sure if it can or it cannot. I think, for example, when humans prove a theorem, sometimes it make analogies. Like when you prove a theorem in this math domain, maybe you have knowledge from another math domain, and they can be there are some analogies between these two, and then you use that domain as a reference. But I think computers are right now not doing that. And
But
also,
you
even
used the notion of domain again, and that was the first question. Are there math domains? Is there a cartographic mapping of maths where there are sort of natural boundaries rather than just arbitrary ones?
I don't think there's a natural boundary. I think the word domain I'm using here are just different topics in mathematics, like algebra and geometry, and maybe more fine-grained topics within each category.
Okay, sorry I interrupted you. You were going to go on to finish.
And also, I think even for the use of geometric intuition, the use of diagrams, although we involve that to some capacity in this project, I think it's relatively less explored in machine learning methods.
I think this was a wonderful presentation, and I'm glad that you're coming back to comment on Steve Wolfram, which is some of these questions are going to arise again there. We seem to have reached a sort of a calm spot for questions, and so I'll give you a rest before you have to do the next job. I have one last little layman's question. I'm not a mathematician. I've often wondered whether a tool could be developed that could search all of the archived, written in some sense, mathematical literature to be able to do a more effective job in determining whether something that somebody wants to prove now has already been proved. Are we closer to that? Something that could be searched for, has this been done before, or has part of this been done before?
I think what the question is, like, you want a better search engine for mathematics?
Yes.
Yeah, I think there are some work in the former domain, like so they are not searching archive, they're like searching Mathlib. So when you want to write something in Mathlib, you want to know if there are existing thing already done. I think there's a tool called Moogle. So basically you Moogle, you replace Google, the G in Google with with M. And so there are definitely people trying to do that. I think currently it's not that active line of research. I think that's kind of related to this mismatched incentive in different community, because I heard from many mathematicians that they think this search engine is really useful. They think it's really helpful. But I think from the AI community and the machine learning people, this kind of topics may be less interesting.
In other words, they don't ask, as scientists certainly do, has this already been done? That doesn't bother them.
I don't have examples for archive, but for Mathlib, it's definitely already done. I think I would say a prototype is already done, and it's definitely not mature.
Okay, thank you very much. I think it was a wonderful talk and I look forward to hearing you again this afternoon.
Okay, thank you. Thank you for inviting me.